All right, let's get started. I'm going to be muting from my mic itself, so frantically thumbs up me or say your mic's off or something if it looks like I'm talking and no sounds coming out. Because I'm going to be switching it on an external mic, which is not something I've done too much before, instead of muting it within Zoom. But yeah, let's look. I noticed there was a question in the Slack, and let me take a look at that. Oh, offhand, there's this plugin for Chrome. It's just a MathJax plugin, which will allow for rendering of mathematical formulas. It's nice to have. Otherwise, the links, sorry, the math won't be rendered in the slides. Or there's actually another way you can view the readmes as HTML, but that's just much more cumbersome. So if you want to see the math rendered properly, go ahead and install that MathJax plugin when you get a chance. Don't worry about doing it right now, but maybe after class. There's a question here. I noticed the README got a serious update. In the vein of resources, what are my thoughts on the Better Explained series? I'm honestly not sure. I'm not familiar with the Math Better Explained or Calculus Better Explained. I'm I can point you at a bunch of math resources that I like, but a lot of those are actually listed in the README. For calculus, I think Salman Khan does kind of an amazing job with calculus. There's also this other professor on YouTube whose name I can't remember offhand, but I'll track down some of his videos. But he just teaches a college class somewhere in the Southeast and posts recordings of his class, and I think those are really great. But yeah, I'm not familiar with the Better Explained series, so maybe I'll take a look at that and give some quick thoughts on it. As far as math for the DSI goes, maybe I'll try to make a more general statement about this. We primarily need you to be competent in Python, and competent to the point where if you're given things that you need to solve in math or things that you need to learn, like say calculus, say linear algebra, you can apply your coding skills in those domains and learn those things faster. We do want you to understand derivatives and integrals, and when you get to neural nets, you're going to be applying the chain rule in backpropagation. There's going to be concepts that you'll want to be familiar with enough that you'll be able to do some light pen and paper calculation when you get there. We're currently working on materials that are meant to be refreshers in those areas. So, how do I say this? More math helps, but math is not your quantitative skills are not necessarily the bar that we set for getting into the DSI, as long as you're able to solve the level of stats and probability problems that we're providing. We assume that you're going to be able to learn enough calculus, learn enough linear algebra to be able to apply those concepts in machine learning, if that gives like a general idea of the level of math we expect. And we can talk more about that. And in fact, we will when we get a little further along. Okay, so yeah, let's go ahead and just start this off. We're going to have our first statistics class today, and hopefully that's not intimidating or scary or anything like that. We're only going to be dealing with one central concept in statistics today, and that's measures of centrality, mean, median, mode, and then we're going to expand on that and get into ideas of variance, ideas of spread. So this is sort of sitting at the bottom of the technology tree of statistics. And we're going to seed this idea because we need you to have an idea of modality and an idea of centrality that that you can program, right? So throughout all the stats materials, except for one class, we're going to be teaching stats and probability through code. So, this involves an analytic approach, an algorithmic approach, where even if you're presented with a problem you don't completely understand, you can kind of bang your head against it with code and get to some kind of solution. And that solution, we'll see when we get there. For today, we're mostly just going to be coding a few functions and talking about these basic concepts in stats. So we're going to kind of have a slow start on this. And in the next class, we'll get a little bit deeper. And then following that, we'll get, we'll continue ramping it up. So when we're thinking about this, why are probability and statistics important? There's a few reasons. And there's a drawing I like to make where, and this is a bit of an abstraction, but let's say you have a whole universe of functions, right? This is our universe of functions, and we're trying to think of any phenomenon as being the result of a function, right? So let's say the number of gallons of water that pass by per minute in a certain section of a stream. Okay, so if we measure that, then if we measure it moment to moment, then we come up with these numbers, right? There is a function in the universe that if we could only extrapolate, if we could only pull it out of the universe and observe it, it might be incredibly complex, but that would be the function that describes the data that we're seeing in that river from moment to moment, that gallon measurement or whatever volume measurement we're making, per second or per minute or however we're deciding to measure that. And it turns out that in statistics, or in machine learning, what we're trying to do is discern some function that's good enough. Okay? So, because we're not going to find the function in most cases. In most cases, the function is not actually a tenable thing, right? We're not going to be able to measure the drip condensation off of every leaf in the forest that's surrounding this stream, and every sneeze a deer makes that sends water particles out and having those condense into the water or anything like that. We're not going to be able to do that. What we're going to try to find is a function within a subset of functions, right, that works. And doesn't just work, it works good enough. And that may not be very satisfying. Let's say this is our function, this little function in here where, actually, let's make that a big X because this is a bunch of inputs, right? We find a function in here that reasonably measures the gallons per minute of water passing by in this stream. And that's good enough. It doesn't mean that there isn't some other function or that there aren't infinitely many functions, actually, that are either in or outside that subset. It doesn't mean that there aren't other ways to solve it. It just means that we find something that's going to work for us and we go with it. Usually this just meets some threshold, some optimal not optimal threshold, but meets some minimum threshold of performance for the business problem at hand, right? That's this process of discovery is a probabilistic process, and if we're dealing with a subset of functions that has an infinite number of functions in it, that is a subset of all functions, then we're trying to discover one function that's good enough. And the way we discover that can be a little haphazard sometimes. More often than not, we have prior knowledge that we bring into the situation, but somewhere in there's almost certainly going to be a probabilistic process upon which we apply some sort of statistical scrutiny in order to discover something that works well enough, right? So that's how I like to explain the why of probability in statistics. There are some other reasons that are pretty important. Data science grew out of statistics as a discipline, and that's maybe an oversimplification. Data science comes out of computer science. It comes out of information theory. It comes out of a whole bunch of other disciplines. And in a way, we can think of data science as an abstraction of the sciences. We can think of experimental design as being very much in the domain of data science, right? So, no matter what science you work in, your experimental design method, your methods of experimental design are also in the domain of data science, right? The reporting of experiments is done through the lens of statistics, right? That ends up being encompassed by data science. Classical models, the classical machine learning models, linear regression, logistic regression, k-nearest neighbor, k-means, there's a bunch of them that are, those are statistical models. And those are also the naive models of data science, right? Linear regression, logistic regression, those are two of our naive models upon which we compare the performance of more sophisticated models like neural nets or, bagging, boosting, these other types of models. Sampling and resampling methods, these come right out of statistics. In fact, one of the books that I link in the kind of helpful links part of the README for our GitHub repository, one of those books is the Introduction to Statistical Learning. Below it is the Elements of Statistical Learning. Both of those books are contributed to by one of the people who came up with one of our very common sampling methods known as the bootstrap. We're not going to talk deeply about bootstrap throughout this course or anything, but we are actually going to, I'm not going to mention when we do it, but we are going to use an aspect of the bootstrap in order to gain confidence in the results of some kind of approximation. And maybe I'll point it out when we do it, but I'll try to convey the idea more than I try to convey the semantics. And then, of course, things like confidence intervals. If you've read published works, published articles, medical articles, results of trials, anything like this, there's always a reporting of confidence intervals. That comes directly out of statistics. The methods of reporting experiments, as I mentioned before, that's straight out of statistics. And then we have concepts of expectation, deviance. All of these things that we use in data science are directly from statistics. Also, a lot of our models use various aspects of probability, right? And you can't really, well, you can try to separate statistics from probability, but at the end of the day, we're sort of talking different sides of the same discipline. So you'll see people describe statistics and machine learning and artificial intelligence. This is kind of a silly comic, but I think the statement on the right here is pretty poignant. So, there's this crack in the wall, and this person frames that crack like as if it's a phenomenon, and it's like, oh, we treat it like a plot, right? And say, yeah, this is machine learning or it's artificial intelligence if you're talking to a crowd. And that I think this is poking fun. But yeah, you'll really find this when you're talking to people who don't know anything about what you're talking about. You'll tend to call it artificial intelligence. And when you're applying for a job, you tend to talk about it like it's machine learning, and or sometimes data science. But data science also sort of sits. That's like when you're talking with the head of operations at a company. You're like, oh yes, I'm a data scientist, and talking with somebody else, you might be a machine learning engineer. And at the end of the day, it's like both sort of apply, or both apply. You just may have specialties in different domains of data science. But yeah, when you get on the ground solving a problem, you're going to be solving it with a model that you have familiarity with in terms of the domain, like logistic regression or a convolutional neural net, or something that where you've built enough domain knowledge and you've built enough familiarity with the model that you can leverage the model within the domain. At the end of the day, a lot of people don't really know what data science is, what data scientists do, and often we aren't great at answering that question either, because there are so many different subfields and domains of data science. So we're going to be just talking basic summary statistics for the first two classes, the first two stats classes. We're going to talk measures of central tendency, mean, median, mode, measures of variance or spread, variance, standard deviation. I would include in here 5-number summary. That's going to be in our notes too. I think it's helpful to see and to be able to program that. So maybe I'll update this note a little bit later. And I think there are a couple questions in here. I think we're good. Okay, cool. All right. So the first thing we're going to consider here is the mean. And we often just call this the average, right? And let's break down this little bit of mathematical formula in just a moment. We've got some symbols here that we use for the mean. We've got mu, the lowercase Greek letter mu. And we use that to refer to a population mean, which I'll, sum up in just a moment. And then we've got x bar, which should be our common form of the mean, and that refers to the sample mean. So I'm going to set this aside, and we'll just think about this over here. Okay, so when we're thinking about the mean, there are two ways we might think about this. If we know every piece of data that exists, like let's say you work for a company that makes screws, right? And although you know the size of every different type of screw, right? You can ask the question, well, what is the average size of screw that we produce, right? You have all the data. All you have to do is go measure every screw and add them all up, divide by the number of screws, and you get the mean. And we would represent that mean as mu because it's the population of items. Now, let's say you choose one screw and you're trying to look for a deviation from the desired size of the screw, right? Let's say it's a 3.5-inch screw, and you expect somewhere between millimeter deviation on either side. And I know I'm switching between standard and metric, but let's just go with it. In that case, you are going to take a sample of the screw sizes, of that type of screw. You're going to take a sample of them. Let's say you sample 10,000 of them. And in that case, you can ask, well, what is our sample mean? You would call that x bar. You're going to add them all up. Your hope is that your sample mean is going to be the actual, like, as close as you can possibly get to the desired length of the screw. I'm assuming you would hope for that. But notice, if this is a sample out of 10,000, you could sample another 10,000 and you're going to get another x bar, right? So x bar is going to have its own variation around some theoretical mu, okay? So if you had the measurement of every screw of this one size that you've ever made, then you could call it mu. But when we're getting a sample, oftentimes we're trying to best approximate mu, right? And so I'm just going to say this, we're almost solely going to be considering things in terms of samples. We're going to be thinking about our desire to approximate what we call a population parameter, okay? So when we talk about a measurement in a population, we call it a parameter. When we talk about a measurement, a statistical measurement in a sample, we call that a statistic. And that's where statistics comes from. It's we've sampled and we're trying to approximate something that's theoretical, some theoretical measurement that's out there in the universe. So let's think about this this formula that I have up here. Let me grab that. Let's kind of decrypt this. If you're not very familiar with mathematical language, this actually is very simple, and I'll illustrate this through a small list of numbers. So let's say we have 1, 3, 7, 4, and 5. We've got this list of numbers. So this list of numbers is, we've got 1, 2, 3, 4, 5 of them. That's what we're seeing here. We're going to start with the first number, right, which is that 1. And we're going to go to the nth number, which is the length of our list of elements, our set of elements, however we want to think about that. So n here is going to be 5. So we can see that this is 1 over 5. And what we have here, this summation symbol, right? This is just adding everything that's in our list of data that we're naming A in this case. So A sub 1 is 1, A sub 2 is 3, A sub 4, A sub 3 is 7, A sub 4 is 4, A sub 5 is 5. So this is going to be 1/5 multiplied by the sum of 1, 3, 7, 4, 5. So, we can do this, 1 plus 3 plus 7 plus 4 plus 5. What is that? 10, 20. That's 20. So this is just 1/5 times 20. And that, of course, is 4. So we have a mean here of 4. So that's a fairly simple operation, and it's very, very simple in Python because we have a function that is just the sum function. So let's see, probably the first thing I'm going to have you do is code the sum function. Let's see if this is coming up next. Oh, but before we get there, there's a concept in the mean. Okay, let's jump back over to that drawing pad. There's a concept that we can apply to the mean where we trim high and low data out of it. So let's say we have a set of numbers that is 1, 3, 4, 5, and let's do 7,000. In this case, if we're looking at this, well, if we add this up and divide by 5, that's going to be, 7,000, what is that, 9, 12, 13, 7,013 divided by 5. Is that number, that very large number, representative of the numbers we have here? Probably not. And, this 7,000 that we're seeing out here, it's not like the others. It's probably anomalous. So what we might do in this case is we might trim out the high value and the low value and just add 3 and 4 and 5 and divide by 3, right? So that would lead us to the concept of a trimmed mean. And depending on how we want to represent this, the trimmed mean either means that we cut out the top top n values, right? Like the top and bottom n values, like the first value and the last value, the first 2 values and the last 2, or it means we cut out the top 10 and bottom 10%. It could mean either of those things. So with that in mind, I'm going to have you code the mean function, and as a bonus, you can put a trim parameter in here that removes the greatest and least n values. Okay, So if we're looking at this is in order, this list of numbers here, A. If your trim parameter is 1, you would cut out this first value and 2000. If your trim parameter is 2, you would cut out your first two values and your last two values and just get the mean of these middle values. So the mean function, all this is going to do is add up all the values in a list and divide by the number of values in that list. And as an optional bonus, you can put in a trim parameter. So let's put 4 minutes on the clock, and I'm going to have you code this out. So I noticed a couple people were slacking me. Needs to be trimmed symmetrically. Yes. Yeah, you trim the top and the bottom end values, or the top 10% and bottom 10%, or 20% or 30%, whatever that might be. Sub I. Let me explain that. So so let's look at this. In the mathematical formulation, we start our indexing at 1. And so if I'm talking about the first element in A, I might call that A sub 1. Now, in Python, of course, we use 0 indexing. So the first item in a list, I would say that's A sub 0, right? So if you hear me say sub, and I can explain this again when we encounter it again. Just bring it up if it's confusing. If I say sub, it usually means it's at that index. Or when we get to dictionaries, we'll see that I mean it's the value at that key. So yeah, I just mean if I say A sub 1, that is the first element of A in mathematical formulation, or A sub 0 is the first element of A in Python notation, or Python semantics. Okay. All right, so I'll leave this in the top right. And you're going to code out the mean function, and you have an optional parameter of trim. Did I go over it in the function? I did lightly. Let's code out the mean function, and I'll explain it in the context of the results of the mean function. So remember, mean is just adding up all the elements in the list and dividing by the number of elements in that list. So you're going to define a function called mean, and that's what it's going to do. So I'm just going to say timer 4 minutes, and go ahead and get started on that. All right, so let's go ahead and code this out. There we go. So I'm going to go ahead and code this with the trim. Well, I'll code this without the trim parameter first, and then I'll add this trim parameter in. So the function itself is pretty straightforward. Mean, we're going to pass in a list, and we're going to, well, I won't put the trim in yet, right? We're just going to sum the list and divide by the length of the list. So the function could be this simple, okay? Let's expand on that just a little bit. And I'll do the mean, and then pass in a list, and I'll set this parameter trim by. And by default, we'll trim by 0. And that just means we're, in that case, we wouldn't trim anything off the top and bottom. I'm going to make a copy of the list. This is because I'm going to modify the contents of the list for what we return at the end. And if I'm going to modify the contents of something I pass into a function, it's just better to make, in most cases, it's better to make a copy when you do that. So let me do that, list.copy, and then I'm just going to do this. If trim by is greater than 0, then we'll say list is going to get the sorted version of the list. And I'm going to only include trim by up to negative trim by. And we can demonstrate what that does in just a moment. But at the end of this, I'm just returning the sum of the list divided by the length of the list, except now it's this list underscore instead of the original parameter that was passed, or the original argument that was passed. Okay, so let's say, what was that, 157? I guess I'll just flip over to it and snag it. Yep. So we've got A right here. And let's call this on A. All right, so let's get the mean of A. And we're not going to trim by anything on our first pass. And then we're going to trim by 1 on the second pass. So this is summary_stats.py. Oh, list and int. Let's, oh, that's because sum, there we go. I had an error. The error I had is that I was trying to include, I was trying to divide a list by the length of the list instead of summing the list first. So hopefully that fixed it. And I'm not printing anything, so let me print stuff. There we go. Okay. So if anybody got anything different from this, let me know. I got 238.3 and 47.75 when I trimmed by 1. And you know, if we're really trying to be representative of this data, is it enough to just trim by 1? And I think in this case we would look at this and say, well, it looks like this is the bulk of what we're looking at, between 7 and 67. 5 is still kind of in that space, but maybe 1 is outside that space. And 220 is, you know, almost 4 times as much as 67. So probably what I'm going to do is trim by 2 to get the most representative mean, which would be a trimmed mean where we've removed the top and bottom 2 values. So that ends up being 26.167. And that does look like it sits right in here, right? That looks much more central than this 47.75, which sits out here, or 238, which sits well outside of where we would think the centrality of the data is. There's a question, do we really need to copy the list? You don't need to, but you should. Part of this is, well, the big part of this is you don't want to you want to be sure about whether or not you're modifying the actual value that's passed into the function. And to get rid of that ambiguity, you make a copy. So think about it this way. If you have a function that exists like this, and you don't make a copy, then there's a piece of data, like say A, that's out here, and let's say you remove values from A within this function. How do you make sure that you haven't removed those values from the original list A? In Python, we tend to not take that risk. We tend to say, okay, well, let's bloat our code just a little bit in order to avoid that. In a lot of cases you won't mutate. It's more about the surety around mutation. So you're not actually the bloat is so minimal by creating another object, because all the pointers are still going to go to the same places, to the same values. So you can make much less ambiguous code by making copies. That's part of the Pythonic ethos around that. Okay. Cool. So let's think about. I believe we've got. Yeah, we've got an applied problem here, and I'll try to fit this in our frame. Okay. So an article published in the journal Indoor Air considers 2 different air samples to test for endotoxin concentrations, the first in urban households, the second in farmhouses. And we've got these concentrations of endotoxins for urban households, right? These are samples, and for farmhouses. Determine the sample mean for the group, and notice I didn't give you a different way of calculating sample mean from population mean. That's because we calculate them in the same way. You add up everything and divide by the number of items. That'll apply for population mean and for sample mean. But this is being explicit in saying we are finding the sample mean because these are samples. And then determine the trim mean for each group by trimming the smallest and largest value from each group. So if you don't have the function I just wrote, let me go ahead and paste that in to the Slack if you want to be able to copy it and use it to answer this question. And we'll take 4 minutes on this. Wait until we get down to about a minute to post your answer, and you'll be able to see that in here. If you notice, I just have a little bash script that will tell us when we're down to 1 minute. It'll say in bold right here, 1 minute remaining. Okay, I'm going to put 4 minutes on the timer, and go ahead and work on this problem. Here, I'll go ahead and paste these in as well. No reason not to. If you want, you can also have the slides open on your side. But yeah, you're right. I should go ahead and paste these in as well when we have them. All right, let's walk through solving this. So I'm just going to make a little section of the code here. Oh, and just so you know, this is synchronizing to GitHub. It's in the src stats directory 01, basic summary statistics. So let's go ahead and do, oops, we'll just make a little section here called breakout, and I'll paste in the problem statement like so. And I'm just going to snag these and pretty directly turn these into lists of what we are looking for. So urban and farmhouse. And currently it's a tuple, but which we could use, but I'm just going to go ahead and transform these into lists. Oh, yeah, and that's another reasoning actually for making copies of things is our function here would actually be able to, well, no, I'm sorry. I was about to make a justification that's not true. Never mind, scratch that. Forget I ever said anything. Okay. All right, so we've got urban and farmhouse. We're going to first determine the sample mean for each group. So let's do that. And let's just print. And I'm sure you've been seeing f strings already. I'm going to be using f strings all the time. So I could print out the sample mean for urban by just passing in, or by interpolating mean of that urban list, like so. So let's look at that really fast. This is sample mean 21.545454, right? Now, we'd probably want to ask, is this meaningful out here to 15 decimal places? Probably not. And why don't we round this to something that seems a little more sensible? Maybe 1 decimal place, given that's what we're seeing up here, right? Well, yeah, let's go with that. And then we've got the sample mean of farmhouse. And I'll just copy that. And we'll round that one as well. So I'm getting 21.5 and 8.6. I think that looks like what other people were getting. Let's just, yep, awesome. And let's do part B. So B was determine the trimmed mean for each group by trimming the smallest and largest value. That's easy enough to do. We can just take both of these and instead of just passing this in, we can do trim by and set that to 1. And notice now we're getting 21.5, 8.6, 17.0, 8.2. So if we set these next to the data, as we can see here, do you think in either of these cases it's helpful to use a trimmed mean versus the mean as it is? What do you think about that? There's a vote for it seems helpful. And this is, we always want to use some measure of critical thought where we want to use some measure of critical thought when we're looking at our data, right? So if we wanted to be a little more rigorous about this, we could probably print out the sorted values for urban. Offhand, notice there is a large value in here, quite a bit larger than all the other values, this 80. And that's pulling our mean to the right. That's my assumption right here, why the mean for urban is different from the trimmed mean, which I should I'll update. I'll put trimmed in there. This 17 here seems somewhat more representative of what we're seeing in urban. Whereas with the farmhouse endotoxin levels, these are relatively close to each other. I don't think we are gaining or losing much between those two values, but definitely with the urban values, because we have this very, we have at least one fairly large value, and then we've got something that might be well in our distribution, this 35, but it still is dragging everything to the right, although there is a 33 in there too. Okay, so yeah, it's just good to use to take a look at your outcomes and think about them. So let me just update this, say trimmed mean. Okay, and I'm going to comment these out so that they're not running every time. Okay. Okay, so now we're going to talk about the median, and the median has a little bit more of a algorithm feel to it in the way that you'd code it, and I'll show you why. So the median is simple; it's just the middle value in a numeric set of data. So let's kind of draw this out. Let's say we've got 1, 9, 3, 22, 7, and I don't know, -4. I'm not going to make a story for this data. Let's just say this is some kind of measurement and it's observable, and that's good enough. So the first thing you're going to do with median is you're going to sort these, right? So -4, 1, 3, 7, 9, 22. And now we look for the middle value. Well, we've got 6 values here, right? So we've actually got 2 middle values. We've got 3 and 7. And so what we would do here is we would take the mean of these. We would add 3 and 7, which is 10, and divide by 2, which would give us 5. And so we would have a median of 5. The symbols for median, the symbol I use usually is this MED. That's what I do, or a capital M. Actually, that's the way I always used to represent median. But MED is pretty common. There's also this X tilde, and I'll be honest, I do not see this very often. You'll usually find this in a specific work, right? There will be some textbook that uses X tilde, and it uses it consistently. But more often, it'll either be the whole word median or MED or a capital M. So median, like I said, it's pretty straightforward. And so we looked at the median for an even set of numbers. If it's an odd set of numbers, it's even easier than that. So let's do 7, 1, 3, 2, 4. And I'll just put these in order. So 1, 2, 3, 4, 7. And then it's obvious what the median is here. It is 3, right? It is the middle value. So we're going to get right into coding this. You're going to code the median function. And you're going to need to make sure you account for even and odd length lists. So you're going to think about how to do that. We're going to take 6 minutes on this one because for some people it's deceptively more difficult than it seems, right? It seems like you can just take the middle value, but you're probably going to want to write this, test your code, write it again, test your code. And why don't we use these two lists? I have an odd list and an even list. And I'll put these in the Slack for you to test against. And I will do that, and then I will set our timer. Okay, go for it. Do your best on this, and then we'll code through a solution. And then we'll take a break immediately after. All right, so I see some good solutions in there, and just scanning through. Actually, give me a thumbs up if you'd like 2 more minutes on this. Yeah. Okay. Let me put 3 more minutes on this. I think it's an important function to play around with. I'll put 2 more minutes, and then we'll get into a solution. So yeah, we'll check back in just a moment. So I'm going to put in the Slack right now a link to the document here that I'm working on, summarystats.py. This is in the source slash stats slash 01 summary stats. And there's also a question, will the code and the slides of the whole course be given to us? Yes, for sure. Here, let me also just link directly to the slides that we're working on right now. Oh gosh, where is that? Just one moment. These are in Markdown on the GitHub, and I'll put those in right there. So that first link is to this. Oh, you know what? Let me give you the direct link here. That first link is to the Python file that I'm working on, which is being auto-updated as I go. I actually have a script in here that syncs up to GitHub every 60 seconds. And so, anything I type here will be in GitHub, fairly quickly. Okay, so I'm going to go ahead and code out this median function, and there are a number of different ways to do this, and I noticed a couple of different ways that are absolutely legitimate. So I'm just going to code it out the way that I think is easiest to explain offhand, and we'll go from there. So the first thing I'm going to do, I'm just going to sort the list, and this also does me, I'm also making a copy in this operation, right? Sorted is going to return a copy of the list in a sorted format. We're not modifying it, but just to point that out, that's what that's doing. And if the length of the list is odd, and I'll do this. I'll say if the length of the list mod 2 is 1, right? If we divide it by 2 and there's a remainder of 1, then I'm going to go ahead and find the index of the middle value, which is going to be the length of our list divided by 2. And then I can go ahead and return list sorted. And then I can, since I have this index, I can just get that value. So that's for an odd list. So let's take a look at this. I'm going to print the sorted version of the odd list, and then I'm going to also print the function call median of the odd list. So let's do that. And let's see what that gets us, just to make sure this is doing what we expect it to do. So here's our result, and I'll blow this up a little bit. If I'm just doing this in a manual way, I'm going to start trimming off the ends of this, right? And we do, in fact, get 14. Now, do we know that this is the 14 we're getting, or are we getting this other 14? Well, we could test that, just to make sure. Let me get rid of one of these 14s and change it to a 15 and see what we get. And we still get 14. That's indicating to me that this is working correctly for an odd length list. So let's also look at this for an even length list, and this is just going to be I'm just using an else here, right? Because if it's not odd, it's even. And this may seem a little funny, but I'm going to get the upper middle index. Okay, so if we're looking at this even list, it's 0, 1, 2, 3, 4, 5, 6, 7. It's length 8. So I'm actually going to get the index. Once this is sorted, I'm going to get the index 0, 1, 2, 3, 4. Okay. And that's going to be the length of the list divided by 2, cast to an int. And then I can just return the mean of the sorted version of the list. And why don't I break this into parts, right? So list sorted, and I'm going to look at the upper mid index minus 1. That's our lower value, right? And our list sorted, really just this whole statement once more, sub the upper mid index, right? So the that's this value, right? This would be 4, and this would be 3. I've got those two values, and I just need to get the mean of those, right? Those are our two middle values. So I can just wrap that in the mean function, which we defined above. So let's see if that works. There's a chance that there's an error in there somewhere. Oh, I need to actually call the function. And I'll call that on the even list. Okay, so I'm getting 12.5. And let's look at this in context. So, right, go through that same reductive process. We're looking at the mean of 12 and 13, which is 12.5. So we can see that that's working as we'd expect it to. And let me go ahead and drop this code in the Slack in case you're not working off of this summary stats document. And I'll just put that in there. Okay, great. So, I'm going to ask a quick question. Oh, you know what? Let's take a break. Sorry, I often will forget. Please remind me if I go, let's say, 10 minutes past the hour, and because I don't want to cheat anybody of their breaks. So let's take 5 minutes, and I'll see y'all back here in a few. All right, let's get back into it. Sorry, I think my cat stepped on the keyboard. So there we go. All right. So we are looking at essentially the same problem that we were looking at before, but now you're going to calculate the median of both groups. And what I would say here is calculate the mean and the median, and give a justification for why either the median or the mean is a better measurement for this data. So let me go ahead and put this in here. Quick. Let me see. I can answer this question really quick. Sanity question: does int round? Int always rounds down. So int is like a floor function, right? So if you have 21.798 or 21.99999 and you cast it to an int, it's going to floor it to 29 just as an integer value. Round, on the other hand, if you perform round without a second parameter like (1) or something like that, it's going to round up to an integer or round down to an integer. Cool. So let's do 3 minutes on this. Get the mean and median of both these groups, and give just a quick 1-sentence justification why you think either the median or the mean is a better measure of centrality for this this general data. So let's do 3 minutes. All right. Okay, let's take a look at this. So I'll just indicate this as a breakout, say breakout, and let's see, let me make sure I'm copying the right thing. Okay, so calculate the median of both groups, and I'm just gonna modify that a little bit and say the mean and median of both groups, and make a brief statement on which is better as a measure of centrality. So I'll go ahead. We already have urban and farmhouse up here, and we already have the function calls. So I'm just going to snag those as well. And I'm going to not use a trimmed mean for this. I'm just going to use a I'm going to use the mean, just the arithmetic mean. And then since I've already got these, I might as well say median for urban and median for farmhouse. I could say sample median, but you know, the only reason, again, why we're using the word sample here is in recognition that these are samples, and it's helpful to realize that, but it's not. It doesn't affect our calculation at all. So let's do that, and let's see. Oh, not timer, but there we go. So let's take a look at these, and I'm going to go ahead and print out the sorted versions of these as well, just to be just to have those in front of us. I think that's generally a helpful thing to have. So I'll print the sorted of urban and the sorted of farmhouse. And let's look at it in that form. Okay, so median is showing us 17, right? And that's, if you recall, that's not too far off from what we were seeing for the, well, I can probably just scroll up and see this, hopefully. Oh, no, I can't. That's not far off from what we were seeing from the trimmed mean, right? And the sample median for farmhouse is 8.9. If we look at where these sit, like let's look at where the sample median sits. That is going to be right here and right here. Now, when we're thinking about the sample mean is up here, right? That's where we're seeing that for urban, and for farmhouse, it's right in here, right? And so this again calls into the question what I think of as maybe outlier data points. And by outlier, I just mean data points that are not representative of our sample, like this value 80 out here. If 80 wasn't here, this would draw our mean back to the left, and it would be sitting close to the median. And I think often that's a good indicator, right? What is the discrepancy between your median and your mean? And that in a sense gives you almost a measurement of discordance in the data, right? Where you have you can almost gauge whether or not you have outliers through some threshold of the mean and median in relationship to the precision of the data. We're not going to get into that so much, but I would make an argument here that the median is probably more representative of our data if we're thinking of this as being a sample taken depending on our sampling methods, right? Now, if we think of this as a purely representative sample, right, where each one of these values, we could fill in, the bell curve to the right and left of it, in order to grow toward what is our actual population. Well, in that case, I would vote for the mean, but just given this, I would make an argument for median. Let's see if there are any questions on that. For the urban farmhouse, you believe mean is the best measure, allows for all samples to be calculated and factored into the equation, and that is a valid argument, right? What you generally don't want to do, you generally don't want to throw data away. You want to qualify whether your sample is representative. And so if we're making the assumption that our sample is representative, and sort of well representative, then I would vote mean as well. Let's see, mean is still the better, comes out to a bit more accurate when you identify the mean compared to the median. That's a good argument, yeah. Although I don't think the deviation of median away from the mean is that much for when we don't have what seems to be an outlier. And then the argument, median kind of gets at the essence of centrality, ignores the extremes. Yeah, offhand, that would be my take. But, without knowing more, without having more information, we can't necessarily be critical enough. But I personally would vote mean in this situation, although I think you can make an argument either way. Awesome. So let's continue forward. And this one should be pretty quick. It's a very similar question. In an issue of a recent magazine reported the following home sale amounts. Okay, that's not the most amazing grammar, but I think we know what it means. So there's this reporting of a sample of homes in Alameda, California, all of which were sold in the previous month. So this is just for 1 month. And these values are in thousands of dollars. So 590,000, 615,000. My assumption is that this is a problem taken from an old textbook, and these are about half what those home values are now, but either way, that's fine. Find the mean value of the homes sold in April, just the standard arithmetic mean, the median value, and make an argument for which is better, which is a better measure of centrality, either the median or the mean. So I'll paste in these. Actually, let me paste them from over here so there aren't any special characters. And we'll just do 3 minutes on this. I think we get the hang of this, the idea of what's happening here. So I'll just do 3 minutes. Yeah, yeah. I think everybody's kind of on the same page here about the median. It really does seem like the median is the better measure of central tendency here, just because we have this outlier, this 1285, this 1.3 million dollar home. So let's go ahead and just solve that really quick. Just paste in the problem. And grab the data, and we'll call this, we'll just call it house prices. And the first part was find the mean value of the homes sold in April. So we'll answer that, and then we'll answer find the median values. And then we're just wondering, is mean or median better? I think it's pretty clear. Median because of the extreme outlier. So finding the mean value of the homes, that's easy enough. As always, I like to print the sorted version of the data, like so. And then I can just say, well, here's an F string. The mean house price is, I'm going to go ahead and round this. I think it's, in general, when you're reporting on these things, be thoughtful of the level of precision and the way that computers sort of, how do I say this? Because computers are discrete machines, the meaning, when you start getting to the right of the decimal to a certain degree, you start losing meaning. So in this case, I'm going to round to 3 places, but probably 2 would be more appropriate, actually. Just do that. Okay. So let's look at that. So is that what everyone else is getting? 620.5 and 582.5? I'm assuming so. Yeah. Okay. Right. And so when we're looking at this, 620 is all the way out here, right? It even just looks to the right of what we think of as being central in the data. And 582.5 looks like it's, right there. So yeah, it looks like, that should say median right there. It looks like the median is clearly the better value here. So let me change that. Okay. Just going to comment these out. Okay. So what you're probably noticing here, and what we've been alluding to, is that the mean is not resistant to outliers. If you have an extreme value, an extremely large value or an extremely small value, that is going to affect the measurement of centrality in your data. And so when we trimmed out extreme values, when we trimmed out the upper and bottom 2 or 1 or 10% or something like that, we do something about that, right? We're making a critical choice to narrow in what we think of as being central in the data. So we think of the mean as being not resistant to outliers, and we think of the median as being resistant to outliers. The only 2 values that matter, the only value that matters in the median is that middle value, or the 2 middle values of which we take the mean, right? We're not taking into account these extreme right and left values. So, as we saw in this data, in the 2 data sets that we've been looking at, it really is dependent on the data set, right? Now, if either of these, like let's say, if we know more about the house prices, right? If we know in general that houses in Alameda in any given month, if every month has the sale of a 1.1 to 1.5 million dollar home alongside these less expensive homes, then we probably want to include that in our idea of centrality, even though unless we are thinking of our monthly home sales as being a sort of population. I mean, in this case, we are definitely saying it's a sample, right? Because we are likely comparing it to other months. But if we want to consider it solely as the month of April, well, it wouldn't make sense to use median there. It would make sense to consider centrality as being this thing skewed to the right. You know, if we're thinking about, well, what's the average of money that you make every month? That would be another scenario where we would want to use the mean. If we know that we are going to be selling every month, a 1.1 to 1.6 million dollar home, that changes the way we think about it. So we want to always be informed by our data. We don't want to think of numbers as being in their own little vacuum and being the source of critical information. We want to think about the actual phenomenon as being the source of critical information analysis. Okay, so let me just make sure there aren't any other questions in here. Let's see. Okay, awesome. So the other, the last measure of centrality that we're going to think about here is the mode. And I'm going to be using a phrase very often. I'm going to be talking about the modal value. I'm going to use that phrase a lot. And I'm going to use it not necessarily in the context of finding the most occurrent piece of data, right? I'm going to be using it to describe in a probabilistic process essentially what your expectation might be, right? Like if you are drawing from like a bowl of numbered balls, let's say, and you happen to have 30 in there that have the number 7, and maybe 10 that have the number 6, and 5 that have the number 4, and 1 or 2 that have the numbers 12 and 13. Well, the modal value, the number that you are going to expect to pull out of there is going to be 7. And I want to distinguish this from the idea of an expectation, which we'll talk about later. But the value that you would expect to get is a 7, because that is just the prevalent value there. And so I'm going to be saying this phrase modal value quite a lot. And what I really mean is it is the most occurrent item if I use that language. So cool thing about mode, and this is very important, we can apply it to categorical data, right? So far, and I'll make this distinction, we've been looking at numeric data, right? We've been looking at values that are essentially measurements. And when we're thinking about measurements, well, we can take an average of a measurement. But let's say you have 3 different sports that people like. You can't take an average of soccer, right? You can't take the average of soccer, baseball, and lacrosse or something like that. What would that even mean, right? You can't sum them together and divide by all of them. It doesn't really make sense. So mode comes in handy for a lot of purposes. I'm mostly, like I said, going to be using it in the context of modal values in the analysis of probability distributions when we get there. But let's think about this in terms of something relatively simple. Let's say people have pets, and people, let's say, have cats, dogs, and snakes. So we are sampling across 10 people, and it's cat, dog, dog, cat, snake, dog. If we're looking at this, well, the most occurrent item, our modal value, our first mode is going to be dog, right? We're going to expect, if we go out into a crowd and ask somebody, hey, what kind of pet do you have, that they're going to have a dog, if we consider this to be a representative sample. They're not going to have, 6 point, or 5.8 dog. They're going to have a dog. So we're going to write a function for mode, and we're just going to get the first mode. What this function is going to do, given a list of items, it's just going to return the most common item. Don't worry about the second mode, or the second most common, the third mode. If you have 2 items that have equal occurrence, just return the first one you completely count. We'll approach it that way. We're going to be very simple about this mode function, and I'll give you a little bit of data to test against about. I've got a list here, and I'll just put this in the Slack. Oh, I should probably put that in. There we go. So you can copy it without the special characters. Okay. All right, so I have 5 minutes on this. Why don't we do 4 minutes? I think this should be pretty straightforward. And we'll wrap up with we'll start talking about sampling a little bit, and that'll inform our next lecture, which will be on measures of spread. So I'm going to put 4 in here and go for it. Try to code the mode function and do your best on it. We'll go through a solution right after. Okay, let's code this out. There are a number of different ways to code this function. So I'll just say that first. What I'm going to do here is I'm going to take a simple sort of switch accumulator approach, which just means I'm going to assume that the first item is the most prevalent, the most occurring, and then I'm going to check the counts of subsequent items, and if any subsequent item occurs more, then I'm going to replace the most occurring item. So I'll pass in a list, and I'm just going to call this most occurring, and like I said, I'll start at the 0th item, and I'll say for each item in the list, and I might as well start at the second item. I don't need to start at the first one, although it won't make a difference in terms of either runtime or the what our algorithm does. If the count of that item in the list is greater than the count of the most occurring item, notice I'm not saying greater than or equal to, I'm saying greater than, because if we have two modes, if we have sort of a purely bimodal, where we have two items that have the same counts as each other, I'm going to just take the first one that occurred the most, right, and not replace it if I find something else that occurs the same amount. You might want to think about how to make this function better, so you get the first mode, the second mode, or you get you get two modes if you have two equal counts. But yeah, in this case, I'm just going to update most occurring with that item under that condition, and then I can return the most occurring. So there are a number of different ways to do this, and this is not the best way, but this is kind of the basic algorithmic way that you would think about this. It's kind of a simple swap, right? All right, so let me copy in that list, and when we're looking at this, looks like Muskrat is clearly the mode, so let's make sure this is working as expected. Mode of the mode list. And yeah, and we're getting Muskrat. Okay, awesome. So there's one more short topic. This is kind of a lead-in topic before we wrap up, and I think that's there are two more things, but I think we can leave the next one for next time. So I want to talk a little bit about sampling, right? If we think about sampling just in a very simple, abstract way, we've got a population of data. Let's say this is all the heights of everybody in the world. It isn't practical to come up with the average, to come up with the mean for all the heights in the world, or the median for all the heights in the world. We're not going to do that. We're going to sample, and this is going to look a lot like that function space that I described, because it's the same idea, right? We get a sample, and we try to make this sample as representative of the whole as possible. And so maybe we sample from all these different places if we're assuming that this larger green circle has, if an item, let's say, here is more similar to an item right next to it than it is to something over here. Maybe we want to sample from all over this space. Maybe that's what we want to do. But at the end of the day, we're building a sample from a population, and that's kind of what we're always doing, right? So we want to make that sample representative as possible. And often we will sample and we'll resample. And we've got sampling methods, we've got resampling methods. Those are, outside the scope of this course, but I am going to point you at a book that builds more of those foundations. And we'll talk about that when we get to cross-validation on the second to last day or third to last day of class. But we are often, as I said, trying to approach some kind of population parameter. And we are doing that, and I say often because you don't want to get too hung up on this idea, but we're often trying to approach a population parameter, or we're trying to discover a usable statistic. And those two things are not always the same thing, as we're going to see as I'm going to allude to with Bessel's correction in our next class. But yeah, so we have these sample statistics. And in an ideal world, these sample statistics would be good approximations of the population parameters. So let's think about this in code. And I'm going to try to code this really quick. I'm going to kind of code a sampling process. So let's do this. So let's call this a quick sampling process. I'm going to make a range from which we're going to sample. Okay. I'm going to say, how about this? Let's do our sample range is going to be taken from the values 0 through 99. And I like using this semantics, this syntax, 99 plus 1, just indicating that we're including 99. I like doing that. Obviously, I could put 100 in here, and as long as we know we're being exclusive, it's fine. So to sample from here, I'm going to use the choice function from random. So from random, I'm going to import choice. And now let's do some sampling. So I'm going to build some samples, and I'm going to just build 5 of these. So I'm going to get 5 samples. And let's look at the variability. Not ramples, but samples. Samples.append, and we'll take a choice from the sample range. So notice we're doing this 5 times. We're putting 5 items into samples, and those 5 samples with replacement, right? So we can get 1 5 times in a row, theoretically, or 50 5 times in a row, or 79 5 times in a row. I'm sampling from 0 to 99 5 times. So if I print our samples here, and maybe I'll just sort these just because, I can print the mean of our sample range. The mean of our sample range, which is, you might take a guess at what the mean of the numbers 0 through 99 are, or what the mean is for the numbers 0 through 99. I'll take the median of this. I'll take the mean of our samples and the median of our samples. And let's see where we end up with this. So if you notice, we sampled 6, 55, 63, 86, 96. And we have a mean between, I should really reorder this, shouldn't I? Let me put this. Our actual mean of the population is 49.95. This is our mu, right? And if we look at our x-bar, 61.2. Well, that doesn't seem so bad, right? That's not the worst. And our median is 63. Well, okay. Let's do this again. So again, the mean of our samples is, this is still in kind of a weird order, but so the mean of our population is 49.5, as we know, and we're seeing a mean of our samples at 74.2, right? So here in the samples, and 76 obviously is our median. So what's something that I could do to have a better estimated mean, or have a better sample mean? What's one thing that I could do to have a sample mean that looks more like our population mean? Any thoughts on that? Yeah, the first thought, and very clear thought is take more samples, right? Instead of taking 5 samples, take 50. That would be a place to start. And this is the biggest issue we run into. Let me be careful about saying this. One of the biggest issues we run into in data science is we don't have enough data, or we don't have data that's in the right form, or we don't have the right data, right? And so you might wonder, well, what do we do if we can only get 5 samples at a time from this population, right? If you can only get 5 samples at a time, and you're doing this every week, right? Then what do? It changes your strategy a little bit. Maybe in that case, we update our belief week after week, and we include prior data in our upcoming data, right? That might be a thing to do. And keep in mind that in statistics, we don't know the underlying function. Here we do. Here we know that there's this sample range, right? We know that there's this sample range that we've defined. We've defined the phenomenon. But what if we don't know the underlying function? What if we don't understand the function of the phenomenon we're observing, right? Well, we're trying to figure that out. And we're trying to figure out measurements in that regard. We're trying to figure out really everything that we can, given limited scope or given limited perception. And so very often what we're really doing is we are strategizing better ways to observe what we're able to observe, right? The data that we're actually able to gather and look at. So we're going to take that into account in the next class, which is going to be expansion from measures of centrality to measures of spread, standard deviation, variance, 5-number summary, variance, and standard deviation, and we'll go from there. Cool. So thanks so much, and I will be teaching Monday. Clark's going to be teaching Saturday. I'll be teaching Monday. That's the lecture for today. Stay on if you have any questions. I'll stay on for about 15 minutes and answer questions. And thanks so much. Have a great night. Feel free to sign off.